Hello, everybody. So this is a demo about symbolic regexes with emphasis on matching and analysis. And the talk is divided into two parts. First, I will talk. My name is Margus Vianes. I'm researcher at MSR RISE. And then Caleb will talk. He's from University of Pennsylvania and is interning with me and Nikolai. And the first part of the talk is going to focus on the use of symbolic regexes in the context of matching. And here I am collaborating with Olli Sargi, who's also a researcher in our team. And the second part of the talk is about integrating similar techniques into SMT solver, Z3 in this case. And this is ongoing work with Caleb as my intern and Nikolai's intern, and he's going to talk about that. So we'll first try to motivate what are symbolic regular expressions, what are the derivatives, why are they interesting, and then we talk about these two parts separately. But the common theme would be then use of symbolic derivatives. So if we look at what is a symbolic regex? Well, regexes in programming languages are already symbolic. There is nothing new in that. I mean, if you look at singleton sequences, they are talking about predicates and not about individual characters. So in that sense, there is a mismatch, in some sense, between classical theory, which wants to treat the alphabet explicitly and talk about single characters one at a time, and applications where this is not really done. And suppose you have an alphabet like Sigma. Well, Sigma here could be ASCII, or it could be Unicode. If it's Unicode, it has over 1 million characters. So if you look at the regex like R below, then one of the questions that arises in analyzing this regex is what are its derivatives? And derivatives are essentially cases of interest so that you can analyze and explore it lazily. And in this particular case, if you want a classical answer, well, there are exactly as many cases as there are characters in the alphabet. In this case, there would be, let's say this ASCII would be 128 cases, or Unicode, several more. But in reality, there are really only two cases that you care about. Namely, if you start analyzing this regex or taking a derivative, making a step in this regex, you have two cases. Either you start with a lowercase letter, or you start with something that is not a lowercase letter. So if you start with the lowercase letter, then the rest of the language accepted will be either you loop in R, so you stay in R, or you consume the first character in the rest of R and continue in the final loop, which is digit or lowercase letter. And if it's not a lowercase letter, you just stay in R, stay in the same loop. So that's sort of the derivative-based view where you incrementally create the automaton, so to speak, underlying regular expression. So in general, there are different ways of doing matching, and one of the more attractive views is to avoid backtracking and instead create the DFA either up front or on the fly. And there are several known like evil regexes that one can see where if you would try to do backtracking, you would really get really poor performance. I mean, even this one I think is, if you take it and paste it in .NET regular expression matcher and try to run it, you will get the behavior similar to what I've shown here on the right. Whereas in fact, if you unwind it as an automaton, it's really quite small and compact. It doesn't have that many states. So there is really no need to do the backtracking based matching here. The problem though is that you would never know if the DFA would grow or grow out of bounds. So you want to, if you know, of course, up front, if it's a very special class of regexes, you can create the DFA up front, but in general you don't. So you want to do it lazily. And that's where the derivatives come in. So you kind of incrementally add new states based on what input you've seen so far. And then you cache old states and try to reuse them whenever possible. So, so I have a technical slide here, which gives a little bit of content of how the derivatives are constructed formally, but I will not go into details of that. I just want to highlight it on this example that if you are given a regex, then one way to construct derivatives is first collect all the predicates that occur in this regular expression. Then in this case would be 3 of them: true, then phi, which here stands for the letter predicate A to Z, and psi, which stands for the predicate digit or lowercase. And then out of those predicates, you would then construct what we call mean terms, which, if you imagine a Venn diagram, would be the non-empty regions of the Venn diagram, or the overlaps that matter. And then using these, essentially like a finite alphabet, you can now construct the derivatives based on those as letters. And there is some technical details, but essentially the unwinding of the derivative would now, or the regular expression would essentially look like, based on the different cases, you would construct new derivatives, and those would become new states that are again explored, and so on. So, so why is that relevant for us? So one of the applications we've been looking into is regex-based match generation in the context of credential scanning. So there is a tool in Azure called CredScan, whose purpose is to find credential leaks. And it's essentially looking for things that people may have forgotten or added deliberately in files, but they shouldn't have. That would then potentially leak information about passwords and stuff. And one of the key things there has to be that the performance needs to be predictable. So there shouldn't in particular be any backtracking used. And they are kind of tricky. Some of the regexes are fairly tricky, like the Unicode character class W, which is actually a pretty big character class in itself. Or, you know, some patterns use non-trivial counting, like the one shown in the second bullet here. So you want things to be lazy. You don't want to create and unwind an automaton here up front that has 20,000 states. That wouldn't scale. So in general, there is a wide spectrum of regex matching techniques. And essentially, there is a trade-off between pre-processing cost and matching cost. So if you want to be really cheap in pre-processing, you just use the abstract syntax tree and you do backtracking-based matching and use the regex ASD as is. If you want to minimize the pre-processing cost, you will try to attempt to pre-compile the DFA and use it. And the sweet spot lies somewhere in the middle, where you maybe try to do DFA on the fly, but then you maybe fall back on an NFA if that doesn't scale. This is a strategy used in many state-of-the-art solvers like RE2, grep, and others. So on top of that, you also have the problem of counting. So you can add counters essentially. Instead of having just a cleany star, you can have an upper and lower bounds of how many times you iterate. And that's another layer of complexity. And even that can be solved partially by using sort of conditional statements that don't explicitly explore the counters. But that is outside the scope of this talk here. So, and then on top of that, one also wants to do determinization of the NFA whenever possible. So the context that I mentioned of this work is credential scanning. And one of the slides I'm pulling out for is by Arvind Ravi. He's Azure, he's working in Azure, and he presented the talk on RSA last year. And it's borrowing this slide because it kind of highlights one of the things which I was surprised about, is that 100% of the red team incidents turn out to lead to credential leaks being the origin of the leak or origin of the problem that they're solving. So it's a highly important problem, and it occurs in different parts of the development. So the tool that I'm going to show you and demo you later on in this talk is being used inside the credential scanning engine as a way to match regexes, and it's applied to different kinds of documents. So it's used both in the server side and the client side, and the usage scenarios are quite different. in this case, the picture illustrates something that you would be running the matching engine, and then there is a file where someone has stored an RSA private key. So there would be a regular expression depending on that usage, then trying to detect these sort of cases, and then you're not allowed to say check in your file or push an edit or something if this credential leak occurs, and you have to fix it first. So the whole engine that I'm going to talk or demo you about is really based on this idea of incrementally creating a DFA, or potentially also an NFA, but here it focuses on DFAs, where you create one state at a time, and the state is a regular expression itself. What is kind of nice about this way of thinking about DFA and regular expressions is that it works kind of smoothly with other operations that usually are not supported in regular expressions, or not at least in known engines that do matching, and these are intersection and complement. And also because we are using the .NET parser in the front end of this matching engine, we get all the bells and whistles of the front end parser itself, which is supporting all sorts of things like case insensitivity and things like that. Overall, because there is one state, sorry, I need to close my window. There is one state created at most per input. There can be at most as many states in the automata as the length of the input. So it's by definition bounded linearly by the length of the input. Regarding the matching semantics itself, what we do when generating matches is a way of eager, non-overlapping earliest matching. So you discover a match, but you try to eagerly find the first one that occurred, not the leftmost one, but the first one. So there are some practical and theoretical challenges in this space also. A lot of things have to do with how to efficiently treat counters. So we have a partial solution to that. We are working on it. But there are also other questions, such as how to deal with anchors. So anchors are frequently used, but they don't really have clear semantic meaning in the context of derivatives, because anchors don't talk about a character. They talk about shift of context, like /b would mean there was a non-word character followed by a word character. Start anchor would mean that there was a new line. The previous character was a new line, and so on. And then there are also other questions like what is the relationship between derivatives of R and the reverse of R? Reverse of R comes in many different disguises. In particular, in matching, reverse happens because the whole matching process is actually a three-phase process in general. You go forwards with a dot star version of a regular expression, then you go backwards with the reverse of the regular expression in order to find out where the match started. And then you reuse again the original regex to find where the match ends eagerly. So there are three phases, and they have slightly different purpose each. So just to give you a kind of a flavor of how that, what the running mechanism actually is in the tool itself of the matcher, is that first the predicates are essentially analyzed. The regular expression is analyzed and mean termized, so you create a smaller alphabet, which is now based on how many mean terms you actually needed. So in this case, if you have a regular expression that looks for a tag, you would actually care only about three cases. Something is a left greater than symbol, something is a left than symbol, or neither. This would essentially translate into three abstract characters or regions of characters. And these would be encoded in the 3-bit bit vector. And now the symbolic part of the regular expression will essentially have predicates that are bit vectors, where, in this case, for example, this regular expression originally translates into this R prime version, where the components are really these bit vectors. Like, for example, 0, 1, or 2, it means all these regions are possible. It would be 1, 1, 1, the true predicate. And this is now optimized and used in the matching engine in such a way that the input is now incrementally mapped into this abstract alphabet, and the regular expression itself works in the abstract alphabet level. So if, for example, your input would be full bar or A, and then tag full followed by bar, you would on the fly create this sequence of IDs for these letters, and the regular expression would work on that level. So in particular, for example, if we start here and run this example incrementally, we would see how that happens. We have initially state Q0, read 0. We enter into state Q2, Q1 with input 2, and 0 to Q1, Q2, and then Q2 loops, and then Q goes to Q3, which is the first time we enter actually a final state. And then we make progress, we have another final state, and then we actually exit the final state. The procedure is a bit more complicated, but now we know, in this particular case, we would know that the match was the yellow highlighted area of the input. But in general, we would have to walk back and then record or find out where the actual match started, and then go forward again to know where it actually ends because of the eager loops. So we evaluated this. This is essentially summary from a paper from Takas last year, where we evaluated the tool. And one of the interesting things about SRM is it has fairly stable in its performance. And I think one of the reasons behind this is it's does not depend on case insensitivity. In fact, when you do case insensitive regular expressions, you tend to introduce fewer cases, and fewer cases means that this abstract alphabet is smaller and the algorithm is more efficient. Whereas in general, if you deal with the matching and you have case sensitivity, it adds an additional layer of indirection where you have to go through tables to decide, which are the case insensitive equivalent parts of a given letter. So here is a demo that I will show, and this is now exactly this file will be run. I'll just go through a dry run here first. Is that it's a C# project where you point to the SRM package, which exists as a NuGet package. You just link to it from your project. And then here I wrote a simple helper function, which in some sense is very special here because it shows the use of intersection. So .NET regular expressions do not have a separate possibility to write intersection. However, they do have conditional derivatives. So most match engines don't really support that, but .NET does. So in this case, if you look at the way the intersection is performed, you can see that, say, if there will be two regexes, then there is a construction of an if then else, where the condition mark, the 0 part of the intersection, is the first argument and the 1 is the second argument. And in this way, you construct an if then else that says, if first regular expression, then the second regular expression, else false. And this is equivalent to the conjunction of the first and the second. And this this sort of special form where the second argument of the conditional statement is false is recognized specifically in the engine and is translated into conjunction. And so if you would, for example, run these several regexes, they would find the match that matches all of them simultaneously. What is interesting here is to note that these are really difficult to write if you would want to write a common regex that matches all of them, because here we talk about for example, a match that tries to find a password looking in some arbitrary input string. And the password would have to satisfy the constraints, in this case, that it has 2 digits. So that's the first regular expression in the end. It has at least one lowercase, the second one, and it has at least one uppercase, third one, and then its length is between 4 and 5. So this is really simplified down to some, demoable size. But then the input would actually find that there is such a match, and this matches method would then find all the matches. And in this particular input, you would see this one. Actually, it's shifted. It should be PW0R1. That's the match that is found. So if we do that, let me see now. If I can share my. So is this screen still shared?
Yep.
Okay. So I'm trying to do the demo, but now I need to actually share. Okay. Interesting. Okay, so the intent for me was to demo the use of this, essentially exactly the same file that I showed, but showed to you from the point of view of Visual Studio solution. So I have a project open here, and I'm just trying to share it, and feel like a bit clumsy here. Okay. Okay. I'm not able to see. How do I share this?
Marcus, why don't you try unsharing, and then when you share again, just select the app you want to share.
Okay, so I do stop share.
Yeah, and then try to share again, and then select.
Okay. Okay.
Yeah.
So now would be this guy. Share. Okay. So now I'm sharing the Visual Studio project, which is the. Let me move away some of them. Which has the program that I just showed you. And what I wanted to highlight is that the using statement, and then in the way you add a link or reference to the NuGet packages, you just either go through the project or the solution and manage NuGet packages, and you browse and you write SRM, and this guy should pop up, and then you just add it to your project, and then you put the namespace here, and you can write as usual. So, and here, if we would run it, let me just stop, put a breakpoint here. Okay, you don't see the output window of what its console output, but it doesn't matter. So here you would have the regular expression running the matches, and the matches, in fact, will not include the match string itself, but it will include the index of the start index and the length of how many characters was in that match. And then you can take the substring of the input to find the actual substring that corresponds to that match. So it's a lightweight match object, so to speak. Yeah, and so if we can. The idea was for me actually to play around a little bit here. Say if I don't care about, suppose my constraints would be just 1 digit, then my regular expressions would look like this. There is at least 1 digit, at least 1 lowercase, at least 1 uppercase, and then 4 to 5 letters. And we can again run this and see what we get. And then the logic of the the analysis a bit different then, because first of all, the match is maximized. The length of match is maximized within these constraints because everything is eager in our case. So, and it tries to find the earliest match. And the earliest match that actually satisfies all these conditions in this case actually starts with at index 4 and ends at index 5. And sorry, it starts at index 4 and is length 5, which is 0, 1, 2, 3, 4, which is S, and has length 5. So it goes over to 0. So it's the subsequence SXPW0. And for some reason, there is another match, which I didn't expect, but I edited this. Okay. But I will not investigate this at this point. Why is it the case? So yeah, so that ends the demo part, in fact, and I'll just have some concluding slides in general. So I need to stop this share, and I will share my other screen back again, which is yeah. And so that was the demo that you guys just saw. And then we have some properties of SRM. Essentially, it is a faster engine than the built-in .NET regex matcher, but it doesn't have all the features, obviously. So it doesn't have, currently anchors are not fully supported, as well as non-regular features like back references, things like that are not going to be supported. It has good performance. It's comparable to RE2. It's more predictable than RE2 in the scenarios we've looked at. And it's drop-in replacement for the built-in regex engine. And the open source implementation is in this project, automata.net project, which actually has SRM also as a sub-project. So this is a bigger project. Has some other stuff as well. And with this, I'm actually done, and wanted to shift over to the use of symbolic regexes in the context of an SMT solver, which Caleb will talk about. But at this point, it would be good if anybody has any questions, because the other part of the presentation will be quite different.
Any questions on the matcher? Okay, I think I can go ahead then.
Okay, yeah. I think we're pretty good on time otherwise, right?
Yeah. You have to unshare your screen.
I see, sorry. Yeah, I will do that. Okay.
Okay. Just a second. Okay, Marcus, can you see me and hear me okay?
Yes.
Okay, so
and I
that
can see the slides also.
Everyone else can too. Great. Okay, so this is the second part of, thanks everyone for tuning in. This is the second part of the presentation and demo. I'm going to tell you a little bit about what we've been doing recently with symbolic extended regular expression analysis inside Z3, the SMT solver Z3. So first, to motivate, why we're doing any of this, basically, I wanted to overview some of the applications of regex constraint solving. And Marcus was talking a lot about the applications of matching. So matching, this is useful in problems where you have where you can specify the verification problems, where you can verification tasks, basically where you can specify what you want to verify as a regex. On the other hand, we have solving where these are verification tasks where the regex is actually the program component under test. So and the specification would be something much more general and complex, like correctness, test coverage, or security. So regexes are very widely used in programming, but very hard to debug. So they're a great example for like a great target for formal verification and correctness. And in order to do that, you need to have a good solver for programs involving regexes. So an example of where solvers for regexes can help is in AWS. So AWS actually, AWS access policies that control whether secure resources get, who has access to secure resources, use a kind of a primitive form of regexes. And they've seen a lot of success recently with this tool called Zelkova, where they actually analyze the regexes in these policies to determine whether, for example, you accidentally allowed like the public to access your private data. So this is an example of where regexes occur in the wild, and an example of where regex solving can be used. Okay, so the project scope that I'm working on during the internship this summer at MSR is within Z3. Z3 is a huge project. It has, this is how many lines of code it has. Within Z3, there's a small part of Z3 which is the sequence theory, and that's the part of Z3 that's responsible for solving constraints involving strings. And within the sequence theory, there is a formalization of regular expressions, and should stop moving the mouse. Formalization of regular expressions, and those are, regular expressions are essentially just constraints on sequences. So in order to build a solver for regular expressions and target some of the applications like what's happening at AWS and other, and in general verification of programs involving regexes, you need a good regular expression solver. So the goal of this work is basically efficient solving of regular expression constraints, and it's in this very small piece of Z3 that we're working. Right. How can we efficiently solve generalized symbolic regular expression constraints? Those are the, I haven't said what generalized and symbolic mean, but that's kind of the motivating question. And there's 3 parts to this. So I'm to the presentation here. So I'm going to try to motivate why we want symbolic derivatives in the first place, why these are a good solution. Some of the key challenges we've had when implementing these in Z3, and then I'm going to demo what we've been doing. By the way, Marcus, if there are questions, if you can monitor for questions in the chat,
yeah. Okay.
Anyone asks anything. Okay, so let's start with an example. So let's say you have a program involving constraints on passwords. So anytime that, passwords, in order to be secure, a lot of sites implement these various password constraints that your password has to satisfy. So you might have a constraint that says something like your password has to have at least 1 letter, it has to have at least 1 number, it has to have at least 1 capital letter, has to be between 8 and 20 characters, it can only use standard ASCII, it can't equal any of your past 5 passwords, and so on. So suppose this is your list of constraints. This is your list of constraints on a string. Then you can formalize this by writing a regex like this. So here, in this case, you would write this particular regex here. And you might be interested in answering some questions about this. So if you're writing a lot of these, you might want to verify that you didn't write something incorrectly. So you could test, did I make a mistake? Is there a satisfying string here at all? You might also want to check whether a certain list of constraints is stronger or weaker than another list of constraints. And these are things you can do with Z3 now or with other solvers. These are examples of like regex solving tasks. So in this case, you could take this thing that this regex that you wrote, put it into the following program. You declare a password to be a string. You assert that password matches this particular regex, and then you ask, is this satisfiable? And you could hand this to Z3, and you would get back, yes, it is satisfiable, and here's an example string that satisfies this. And the way that Z3 works today, so this is like the existing solution that we're trying to do better than. The way that Z3 works today is by taking this regex that you wrote, converting it to a state machine. Doesn't really matter what kind of state machine, but converting to some kind of state machine. And then the question of whether this thing is satisfiable boils down to the question of course, whether it's a final state reachable in this state machine. So if the regex is satisfiable, that means there's some string that satisfies it, which means there's a path in the state machine that goes from the initial to the final state. And basically all constraints on regexes are solved in this way. So you're just going to start by getting rid of the regex by compiling it down to some kind of state machine representation, and then you answer the question on the state machine rather than answering it for the original regex. But the problem with this existing approach is illustrated on the example of the password constraints that I put on the previous slide. So for this example, for this particular example, if you were to plug this into Z3 and then generate a state machine, here's the actual state machine for this regex. So it's this gigantic thing, and actually, and the question of satisfiability becomes: is there a final state reachable in this big machine? And the result of this is that you actually have basically Z3 will hang because it has to create this giant state machine before it can even answer your question, and it's just going to keep trying to create the state machine without even getting to whatever you're going to ask. So this is like a state explosion problem. And what we're hoping to do with this project is improve on this. So rather than doing a global analysis of the state space, the global analysis of the state space doesn't work because there's too many states. So what we'd like to do is instead apply kind of algebraic and symbolic reasoning about the regex, so to decide if it's satisfiable. And in this case, it should be fairly, it should be a fairly tractable task to very quickly decide if this is satisfiable. And we want to do that by kind of locally making changes to it or locally exploring different possibilities rather than globally expanding it out into some giant state machine, which is intractable. So in particular, if this is the giant state machine, rather than generating it all at once, what we want to do is lazily explore states from the initial state kind of incrementally, maybe through kind of a depth first or breadth first search. You could think about it. And the solution to this, the tool that gives us this kind of search is exactly symbolic derivatives. So symbolic derivatives are what allows you to, given a regex, locally explore states in a state machine. What the derivative gives you is exactly the next states in the machine. So that's why we're using, why symbolic derivatives are a promising idea here, is that if you use them, you can avoid this state explosion problem. So that's symbolic derivatives, and then actually implementing them involves another set of challenges. And I'll just try to, I won't go into too much detail. I'm just going to try to illustrate a few of the key challenges we've had in that we're having in integrating the symbolic regular expression solver, implementing the symbolic regular expression solver and integrating it in Z3. So the first challenge I wanted to highlight is, how do you represent regex derivatives? So what is a regex derivative? Here's the image on the top. If R is the original regex, then the derivatives are like algebraic transformations that give, the derivative is an algebraic transformation that gives you the next states. So in this case, the derivative gives you the 2 next states, and then from here it gives you 2 more next states. So it's really just giving you the state machine that you could have gotten by expanding out globally the entire state space, but it gives you it in this incremental way where it only calculates one state at a time. And the question though is, how do you actually represent these derivatives? And there's a lot of different choices here. So here's the example program from before, this password program. And notice that this password constraints include a bunch of ands and it includes not. So that means we have complement and we have intersection. And actually, in general, we want to support like any number of we want this to be very extensible with a variety of expressive regular expression, maybe non-standard regular expression operators. So for example, reverse, arbitrary user-defined predicates, counting loops. We want this to be general and not specific. So we want to kind of support anything you might come up with as a regex. We want to be able to support it. And we want to then be able to write this regular expression and then take a derivative of it to get the next states. So so here's the derivative, the form of the derivative. It's given an initial character x and a regular expression r, give me all the next states. And a key here is that because we're trying to do like solving rather than just matching, we don't know what x is. So x is initially unknown, and we have to somehow represent this thing in this set of states. Then it's not just a single state; it's a different set of different possibilities in a compact way and in a way that doesn't blow up and that leads to the best empirical performance. So what we're finding is a very effective way to represent this is using if then else expressions, and this is kind of a new idea for how to represent derivatives. If you for example, here you have dot star a to z dot star. That's a regular expression that indicates that matches all strings with at least one lowercase character. If you take the derivative of that classically, it's saying what are the next states, which are either dot star or dot star a to z dot star. But if you use this, if you don't know what x is, then you have to represent it using this if then else expression. So the if then else is saying if the first character is from a to z, then it's one thing, otherwise it's another thing. So you kind of get these conditional these conditionals expressions in your derivatives, and then you have to figure out what is a good way to represent these nested conditionals so that you don't get kind of explosion or so that your representation is compact. So it turns out that this is a really good way to do things. For example, intersection and complement just work out really well on these if then else expressions. So if, and technically the representation kind of has a connection to symbolic Boolean finite automata, which are a form of alternating automata. Second challenge is that everything in this setting, so usually when people talk about classically when people talk about solving constraints involving regular expressions, they usually talk about specific problems like non-emptiness or inclusion, where you know what the input is and you just want to apply, say, a non-emptiness algorithm and output whether, given an input a regular expression, is it non-empty or is it empty? So that's a decision problem. But inside an SMT solver, you actually have to solve a much more general problem, because your SMT solver, your regex solver doesn't just exist in a vacuum, it's interacting with the SMT solver. So if the SMT solver just asks you a question like, is this regex non-empty? You can't just hang for the next 10 minutes and then come up with an answer after 10 minutes, because that will, basically that's useless. The SMT solver kind of has to wait during that time. It can't make any progress on the general satisfiability problem. So what's the model that you have to adopt instead is kind of an incremental model where the SMT solver gives you a constraint. Okay, is this regex non-empty? And then you have to make like a step on that. So you can say, okay, yes, it is empty if it's obvious, or you can say, I don't know if it's not empty, but it reduces to these other two constraints. But you have to perform kind of a very bounded amount of computation and then hand control back to the SMT solver. So everything has to be incremental. And that makes a lot of the algorithms you need more complicated. You can't just plug in like a classical algorithm and have it work. And then a final challenge in integrating with SMT is just general things that come up when integrating with SMT. like the previous slide is one example, but in general, you have to solve a more general problem than you thought you had to solve. So here's the example again. This password has to have at least one lowercase character, at least one number, at least one uppercase character, and between 8 and 20 characters. And the capital A through capital Z, for example, is a symbolic predicate. So it's not a union of all the letters from A to Z. It's kind of a user-defined or general Boolean predicate that can be true or false. And that means that for those predicates, you have to interact with the SMT solver to give you the answers to those or to solve those. Like, is this satisfiable or not? And you want to, again, have this kind of back and forth where you're incrementally computing whether things are satisfied. You're incrementally making progress on the regex, but also asking the SMT solver if the user-defined predicate is satisfiable. And the advantage of this is that it's not just ASCII or Unicode or one particular string representation that we're thinking of. We're actually thinking of regexes over arbitrary sequences. So if you wanted to use Z3 with sequences of vectors and then write a regular expression over vectors, you could do that, and we could handle it ideally. I won't talk about the soundness case on the bottom. Okay, so let me get to the demo. So just to briefly show what we've been doing in Z3, you can currently actually, this is actually currently implemented in the stuff we're doing with symbolic regular expression solving is currently implemented in Z3. So you could download Z3 right now and start using it. It's an experimental feature though that you have to turn a flag on, and probably doesn't always work the way you'd expect because it's kind of all in progress. But let's say we wanted to, I just wanted to show what it would be like to code up this password example and answer some basic questions about it. So let's start by making a file. So I'm going to have this demo folder. I'm going to make a password smd2 file. And I'm just going to answer the very basic question that I was using in the example. So I want to know, is this set of password constraints satisfiable or not? So first I have to declare that password is a string. So password is a string, and I have to then assert that that the password is in a certain regular expression. So password is in the intersection of a bunch of different constraints. So we can play around with what constraints we want here, but for example, we said it was supposed to have at least one lowercase character. So so this is the concatenation. This is the function for concatenation. So at least one lowercase character means it's concatenate anything followed by a lowercase character followed by anything. And a lowercase character is range from A to Z. And that's how you say at least one character, lowercase character. Then we can also say that it should have at least one number, for example. I should put, and then we can add, for now, let's also just say that it has at least one uppercase character and see what happens. So those are our three constraints. We have the intersection of those three. We have, we're asserting that this password string is in that big regular expression. And now we're going to check sat to see and get model. Check if this is satisfiable and then get the example string. So let's see if it worked. So let's see. I'm going to try with both the old old implementation and the new implementation just so you can see the difference. So this is the old implementation. So it gives you, so it is indeed satisfiable, which is good. And it gives you an example string. So in this case, A3S00. Actually, this /x00 is like a particular character, but anyway. Okay, so then to use the new implementation, this is just the current Z3 from GitHub that you can download. We just have to turn this flag true. This is use derivatives. So to be clear, this previous run was using this like automata-based decision procedure where it compiles everything down to a giant state machine, which can blow up in some cases. And what this flag tells Z3 to do is to use derivatives, use the derivative-based incremental decision procedures instead. So you can see that it was pretty fast before. It's a little bit faster now, but it's not really perceptible, the difference. In either case, it gives you an example password that satisfies the constraints. But now let's start to add some other things. So what causes blowup? Well, we know that state machine blowup is caused if you add complement. So let's put in a complement, and let's put this is how you make a regular expression from a string. So I'm going to say that it's not equal to one of my past passwords, and my past password was my very secure pass 10, and this should already cause quite a bit of blowup because state machines do not like complement. But we'll see what happens. Okay, so here's the old implementation. Oh, I actually did. Okay, so it took like you actually put ST to see how long it takes. So it took about 7 seconds, and that's still the old implementation. If we use derivatives, it's about 0.03 seconds. And basically, the more constraints you add, the more blowup occurs. So the other thing that causes a lot of blowup is saying that it's between 3 and 8 characters. So if you say, so the way you use that is with the way you specify that is with a counting loop. I think this is how you specify that. So this is between, let's say, 8 and 20 characters. And all char means a single character.
Maybe instead of all char, you could write the star of A to Z, or the star of visible characters. But that's
true. What's the initial and
the initial character is exclamation mark.
Okay.
And the final character is tilde.
Tilde. In
the visible range. Yeah.
Yeah. Thanks. Okay. So this is loop. This is saying loop between 8 and 20 times one of these characters. So yeah. So here's the new implementation, about 0.14 seconds, and old implementation is probably just not gonna. It's probably just gonna completely hang, but maybe it'll take like 10 seconds. So that's almost the end of the demo. I just wanted to do the full example. So this is, which I've actually done most of it already, but this is the full example. So lowercase letter, number, uppercase letter between 8 and 20 characters. This is valid ASCII, and then this is not equal to one of my 2 past passwords. And here's the Z3 syntax. Yeah, so it's probably not going to terminate. Password full. So now it's, oh, that's the previous implementation. I'm not gonna, the previous implementation again will be very slow and hang. And with the derivatives, it's very fast. So basically what's the takeaway? Like if derivatives do this thing where they just like try a character and then unfold the derivative, try a character, unfold the derivative. And so no matter how many constraints I add, it's going to remain pretty much still tractable. Unless I put some like really pathological, difficult constraints to satisfy, it'll just incrementally unfold it. And having these additional things on here doesn't really affect it. Like if I have these complement, it's not equal to my pass one, not equal to my pass two. This really has no input, like basically no effect on the runtime. Okay, so that was showing that derivatives are fast. Here's just some summary of the performance. Oh, does anyone have any questions or something? You can stop me now if you had a question or something that you want me to show.
I don't have anything in the chat window, but one thing maybe you could mention, I have a question myself, was the role of these Antimirov and Brzozowski derivatives.
Oh, right. So, so this is related to the actual representation of derivatives that you use. So when you're, so in the current implementation, we basically, we use these if then else's. So we unfold the derivative as an if then else, and then we just represented it as basically using the Brzozowski cell, so single states. So determinized states. So you're basically unfolding states of a determinized machine. But what you can do is try to unfold using states of a non-deterministic machine. And that can be, that's something we need to investigate, whether that's more efficient. Okay, that's, so conclusion, basically, our goal is to have efficient analysis of symbolic extended regular expressions, where symbolic means that the constraints, there's kind of user-defined constraints or predicates on characters, and the extended means that we have intersection, complement, and reverse, or any other any number of things that we can add. And I tried to describe some of the key challenges. You can try it out by going to this link on GitHub, and as I showed, using this flag SMT use derivatives equals true. It's definitely work in progress, so you could find a bug or a crash. So, well, if you find something, let us know. Okay, let me. Exit out here.
Okay. So I think.
Very good. This is Tom. Yeah, thanks. Tom Ball from Microsoft Research. This is great stuff. We saw that the open source for the first half of the talk is in the Automata library. This work you're doing, Caleb, is integrated directly in Z3?
Yeah, that's right. I mean, some of it is like not yet in the main branch, but.
Okay, so this is ongoing work, but it will be available. Okay, cool. Great. Last chance for questions. There's one more minute.
It's like 9 p.m. Eastern time, so.
That's true. Okay, I'm going to shut down recording, and thank you all.
Thanks.
All right, thanks everyone for tuning in.
Okay,
Yeah.
bye-bye.
Thank you. Bye-bye.
Bye.